A common way to simulate stock price movement is to use a relationship well established in finance, referred to as geometric Brownian motion. And at the heart of geometric Brownian motion is this idea that stocks move randomly, and we could, for instance, consider the following: that a stock price can where S denotes some kind of asset or a stock price, that a change in the stock would be equal to some kind of mean drift rate times the stock by the change in the time period plus a volatility measure scaled for the stock price, and then this finer process which defines a random normally distributed shock. So if we take this one step further, we could express this in terms of an exponential, where the stock price at some point in the future is equal to the current stock price times an exponential, and then again a mean minus the volatility squared divided by 2 times t plus volatility, and then the Wiener process. And typically we adjust the mean. The higher one of the things, a phenomenon here would be when volatility is quite high, the stock price in these type of processes seems to grow more quickly. And to adjust for that, we normally subtract, this can be shown mathematically, we normally subtract this term away from the volatility term, away from the drift. Now, to see that in operation, how that might work, we could take this relationship. So we might just copy this, copy and paste. Again, maybe I'll paste here. Okay, and we're going to model the stock price in such a way that the stock price in the future, so the stock price plus the change in the stock price, is equal to the current stock price times the exponential. Okay, now we could relate this back to Black-Scholes model and take some of the terms here in this process, geometric process or log normal process. We could look at in terms of the Black-Scholes model. Mu here could be viewed as the difference between the risk-free rate and dividend yield. The volatility figure, or variance here, but the volatility figure could be thought of in terms of the Black-Scholes volatility. The change in the time period, delta t here, could be seen as the periodicity over which we're allowing the stock price to evolve. So are we getting weekly changes or monthly changes or annual changes? Okay, so if we had if we were trying to develop a process over the period of a year and we're considering monthly adjustments, then delta t would be 1 over 12 because it's 1/12 of a year. So a month would be 1/12 of a year, it would be 1 over 12. And the epsilon here is, if you like, a random, it's a random number, but it's also a random number that has a normal distribution. Okay, so let's see if we can first of all understand and develop in a spreadsheet a random number, and then how do we superimpose normality. Okay, so to generate a random number in Excel, it's very simple. We just say equal to random, open bracket, close brackets. And typically we'll get a number between 0 and 1. And if we took the mean of this, so the average of that matrix of values, it should on average be equal to 0.5. So I'll try this again. Average, open bracket, and take the selected. And you can see it's close to 0.5. So if we hit F4, let's try this. If we hit F9, you can see the value here, because it's a relatively large sample size, it doesn't deviate that much from 0.5. If we took a smaller sample size, so for instance, if we took the average of perhaps this small cohort of 6 values or 9 values, we'll get a bigger variation. Okay, so if we write average, which calculates the mean, okay, if we hit F9 for the large sample, and then for the small sample is just a 9. Small sample, if we hit F9, notice there's bigger variation here. So it can deviate very substantially away from 0.5. The bigger the sample, if we make the sample bigger again, and work out this average value. So instead of going to 24, what if we went down to 56? So we have the full sample size, and hit F4, F9. Again, you can see while this one remains close to 0.5, this one deviates. So the larger sample size will produce a mean of 0.5. So this particular random number, you can see the number is random. It probably has a uniform distribution and so on, but it is random. Okay. To convert this random number into a normally distributed random number, we could use the norm's inverse. Okay, so if we use norm's inverse function, so we could generate, okay, we could say a random number. If we write random, okay, the value will if we F9 this, you can see the value will always between 0 and 1. If I put norm's inverse on this, the value then gets converted into having a mean of 0, norm's inverse, mean of 0, and standard deviation of 1. So let's take these range of values again, and we can pull down, and then we can say, okay, what's the mean? Well, if it conforms to standardized normal distribution, then the value should be, the average of this should be 0. So we'll take the full sample and return. And okay, not quite 0, so let's F9 that just to see. Okay, and so there's some negative values and some positive values, but the values are not far from 0. And then likewise, if we take the standard deviation, so we could just copy this, in fact, copy and go underneath escape, paste, and change the average to be a standard deviation, STDEV, which is the standard deviation. The standard deviation generally here is going to be close to 1. Okay, so at first glance, just taking an initial view here, what we observe is that the mean is 0, standard deviation of 1, and every time we hit F9 we re-randomize the numbers and we can see these properties emerge. Okay, so if we wanted to generate a random shock in terms of which conforms to a normal distribution, one possibility is to use the norm's inverse random. Okay, so as a result, we probably could set up a simulation here. So if we go back to a stock price simulation, we could consider the following. Okay, we might say, look, we're going to consider a change. We're going to consider monthly changes in the stock price. So we're going to look at the change in time, the delta t, has been 1 over 12. We could take the initial stock price S to be 100. Okay, we could take the volatility, so the volatility sigma, we might say is 0.2. We could take the, now we have to look at our drift, and the drift we have to represent as the term here in these brackets. Okay, so we could say the drift is equal to mu. Now mu is r negative q, so let's just generate that first. Okay, we need a term for mu. Let's say that's 0.05, 0.05, and we could take q to be just initially 0. So the drift as a result will be open brackets, and following in line here would be r F4 negative q F4 minus 1/2, so 0.5 multiplied by the sigma to the power of 2, and we can divide that. That gets in turn divided by 2 because it is 0.5, and then we're multiplying that by delta t. Okay, so delta t then ultimately applies here. And our drift is defined here simply as being r negative q minus 0.5 times sigma. Sigma is 0.2, and it's been squared. So it's just that term in the brackets represented here. In the next video clip, I'll set out a stock price over a 12-month period and just look at its evolution and then just try to graph that in the simulation.